Hi guys, so as I told you, I'm going to be gone the next 3 days, so I wanted to make sure that we aren't missing out on any instructional time. So I'm putting together these 3 videos that will replace my 3 days in class with you all. Just so you know, the way that this works best is if you have your Chapter 5 notes in front of you and you are following along. If I say, take 5 minutes to do this section, just pause the video and take 5 minutes to do that section. So a little note on this. This is 5.1. You should be doing this on September 13th. The PowerPoint that you're seeing right now is on Canvas. So is the DOL. So you will do and submit the DOL on, through Canvas. And your homework will be assigned on Canvas as well. I will not check homework until the Monday that I get back. So here we go. Have your Chapter 5 notes out in front of you and be ready to go. Again, pause and play. So if I say take some time to try it, please take some time to try it. You are still responsible for this material, so just watching me do it is not going to be helpful for you. You need to kind of understand where things are coming from. Alright, so 5.1. So today what we're going to be looking at is analyzing cubic graphs and identifying relative minimums, maximums, and multiplicities. Some of those words are familiar to us, others are new, but we will definitely learn them. So I would like you guys to take a look at your warm-up for me. The warm-up is right here, but again, you should have this PowerPoint on Canvas, so you can go ahead and pull that up. I'm going to give you guys take about 5 minutes to pause this video and work on that warm-up. Okay? Go ahead. Alright, so the first one is to calculate the y value when x equals 4. If you notice, these y values are going up by 6 each time. So that next one, 40 plus 6, is going to get us 46. And question number 2, calculate the y value when x is 20. I think that's rather difficult to do. If you wanted, so I guess this is going on to 3, there are definitely more than 2 ways to do this, but if you wanted to, do 5, 6, 7, all the way up to 20 and figure out what 20 would be, you can do it that way. I see this, because it's going up by the same amount every time, we know this one's going to be linear. So again, our equation for a line is y equals mx plus b. Now that y-intercept we don't know yet, but if we had a 0 term up here, like if we had x equals 0, well, it would be 6 lower than 28, so it would be 22. That would be our y-intercept. And it's going up by 6 each time, so that's our slope. Well, now that makes 2 a piece of cake, because all we're doing is plugging in 20 for x, so it would be 6 times 20 plus 22. And 6 times 20, if my math is right, is 120. We add those together, we get 142. 142. If my math is ever wrong during these videos, because I often make mistakes, please comment on the video with where that mistake is, so that we can, so that your classmates know. Alright, so next up, if you look in your notes, we've got a problem situation for today. It's called the Plant a Seed Planter Company. Go ahead and read through that description of our problem situation for today. Familiarize yourself with what's going on, and we'll come back and have a quick description about, or a quick conversation about that. So go ahead and read that for me, please. Alright, so basically what's going on here is the same thing we saw when we looked at the drain situation, where we took the drain and we bent it up on the side, so we had like our overall area was determined by the length of the original sheet of metal we were using. If you don't remember that, it's from chapter 4. So basically we've got the same idea going on here. Here's my little post-it note example. It was 18 inches across this way and 12 inches across this way, and I've cut out these little corners. So basically what the problem is saying is that after I cut out those little corners, I can fold them up and we'll have what they're selling as planter boxes. Let me finish folding those up for you guys so you can kind of see. So again, after there it was all cut out, and I just folded them all. And so now I've got this little planter box here. Okay, so you can see that this is no longer 18 inches across because I had to take off those two corner pieces. And this is no longer 12 inches wide because I took off those two corner pieces. So we can see that in our diagram, but I think it's a little bit easier to see once we actually see what happens after we fold it. Now we've got a little planter box. Okay, so we're going to work on this table together, and then I'm going to give you some time to fill out the rest of that, and we'll check and see how we did. Okay, so going back to my little example here, with my post-it note example, if we took 0 inches, so this little square I cut off, if there wasn't anything there, the height, probably make sure this is consistent with what I did earlier. Let me make sure. Sorry, I don't want us to have to switch it again. Alright. The height of my box, once I folded it, would be 0 inches. If I didn't take anything away, I can't fold anything up. So my height is going to be 0. Now my width, this used to be 18 inches, and I took 0 from both sides. Again, 0 because that's how much it's saying we cut. If I took 0 from both sides, it's still going to be 18 inches. And then my length, it used to be 12. If I took 0 from both sides, it would still be 12. That was a silly example. We should probably consider our volume here. Slope and volume, if we didn't remember how to find volume, it's height times width times length, right? Or any combination of those three being multiplied together. Well, in this case, 0 times 18 times 12 is just 0. We've got that there. Okay? Alright, so if we do the next one, this one makes a little bit more sense. If I cut 1 inch squares, so 1 inch here and here, 1 inch over here and here. If I cut 1 inch squares, when I fold those up, well, now it's going to be 1 inch. So that's how tall I made my box. That's the corner length that I cut. So it's going to be 1 inch tall. My width used to be 18. But I took 1 from over here and 1 from over here. That means I've got 16 inches left. And same idea with my length. It used to be 12, but then I took 1 inch from both sides, 1 inch over here, 1 over here, which means I'll have 10 left over. And if we found our volume, we did 1 times 16 times 10. 1 times 16 times 10. We get 160. Okay, go ahead and take about 3 minutes to see how far we can make it through the rest of this table. Right down at the bottom here, it says H. So I'm asking for, in general, how would you find all of these things? For any H, how are you finding the width and the length? Go ahead and take 3 minutes to see how far we get through that, okay? Okay, hopefully we took some time to do that. I'm going to just show you all of my answers. If you didn't get any of them or you messed up somewhere, just ask your buddy or another friend for some clarification. Hopefully they can help you out. But here is my answer. We should notice that something odd is going on down here. Once we start taking away bigger numbers, we start to get these negatives going on. And the reason that I have question marks here is because can you really have -2 feet in length? That doesn't make much sense. And then again, can we have a negative volume? What would negative volume look like? So I've got some question marks there because yes, mathematically those are the numbers we get, but I'm not sure. Maybe those should just be zeros, because what would that look like? I don't know. We're gonna fill out this H table because I think that's probably the one you guys need talking through the most. So I'm gonna put mine back up here just so we can talk through those. Now, we should notice that whatever corner length we cut out, that's how tall our planter is going to be. So if I cut H out, whatever H might be, then my planter is going to be H tall. Now my width used to be 18 inches. That's how big that sheet was. That's how wide my paper was. And then if I cut out anything from over here, we'd have to subtract that because I cut it from it. But I also cut it from over here. So not only am I subtracting 1, but I have to subtract 2 from the original 18. So 18 minus 2h. Pretty much the same idea with the length, except the length was 12. And then again, I'm taking h, my corner that I cut out, and another h, so 2 h's from that 12. And volume was just height times width times length. So now that I know what those are, I can just write them all as multiplication, and that's the function that finds volume for this scenario. Okay? All right. Go ahead and take a look at A and B right below that. A and B, A says, what is the largest size square corner that can be cut to make a planter box? Explain your reasoning. And B, what is the relationship between the size of the corner square and the length width of each planter? Here's the deal. I feel like we've kind of already answered B up here. Okay, put that into some sort of words down here. How does the corner length determine the length and width of each planter box? And then A, what is the largest size square corner that can be cut out? When does it stop making sense to make those cuts? Okay, go ahead and take about 2 minutes to do that. So just pause the video and I'll be right back. Alright, so question A said, what is the largest size square corner that can be cut out of the planter box? Well, if we start looking at where this doesn't make sense, right, we said these negatives didn't make sense, but also these zeros don't make sense. If you've got a volume of 0, that's not a planter box. Okay, so for A, it just needs to be anything less than 6. The largest size square we can cut out is 5.999, right? Anything less than 6 will work, but anything over 6 does not make sense. And then B, what is the relationship between the size of the corner square and the length of each width? We kind of outlined those here. But whatever our corner size that we cut out, we take that away twice from the width and from the length. Okay? Okay, so moving forward through our PowerPoint, there's this slide. We just did that. We did A and B. The next one, we know that volume is length times width times height. Use the expressions we came up with to write the equation. In your notes, that's right at the top of this page. Write the function. So that's where we are. We already did this in our graph. Sorry, I jumped the gun a little bit. So our function that finds volume in terms of height, remember our function notation, that's what that does. It tells us what it finds and in terms of what. We said was our height times our width times our length. And all of those are in terms of h, so we don't have like two variables going on. Okay, that's perfect. So that's where that should go in your notes. And as you can see on the next slide, it says that we're going to use our graphing calculator to graph this and then find these key characteristics. So if you haven't done so yet, pause the video and grab yourself a graphing calculator. I've got mine here. So on your graphing calculator, we're going to go into our y equals, it's this button right here, and we're going to graph that function that we wrote. Now, obviously in the one that I gave us here, I replaced all of those h's with x's because that's what our calculator knows. It knows x, not h. So I'm just going to type that in, x. You can do the times if you want to, and then make sure that you have your parentheses. 18 minus 2x times, again make sure you have your parentheses, 12 minus 2x. You guys a second to get caught up to me, but pause it if you need some more time, or if you need your friend to help show you where any of these buttons are. And we want to look at what this graph looks like. So I'm going to hit graph. Now I'm going to go in, regardless of what my window looks like, and we're going to all change our window together. That's the graph that I've got. But again, my window needs to be changed, like absolutely needs to be changed. So go into your window and do this even if your window is fine, even if the last class already changed it for you. Our x minimum, so we were plugging in x to mean the height. Obviously we're not going to cut out anything less than 0. You can't cut out anything less than 0. And the most that we cut out, at least in our table, was 7. So I'm going to leave that as 10. It's a little bit more than we need to see, I think. Now, I'm going to take a guess here and say that negative 10 will be fine. But if we look at our volume in our table, I think our volume went up quite a bit. Let me take a look. Looking back at the table now, it went up to 224. So I think if we go up to 250, we'll be okay. We might need to go back and change those, that's fine. But if we take a look at our graph, we can see a little bit better what's going on. So we see this goes up far enough to see the important part, but doesn't go down far enough, right? So that means I need to go back and change my y minimum. And y minimum needs to be more than negative 10. So let me say negative 50, which is just a guess. There's nothing mathematical about that. Take a look. Still not down far enough, so let me go back. Negative 100. There we go. Now we're seeing all important parts of our graph. Okay, I gave us some space in our notes to copy that graph down here. So go ahead and do that for me. You might need to figure out where some of these places are. Like you might want to know where it is here or at any of these intercepts. So you can just hit trace and kind of move your little bug around to do that. Okay, so go ahead and pause the video. Go ahead and copy that down in your notes. And then we will move on with some important vocab, okay? All right, I almost forgot. We want to go back and look at these key characteristics. So the first one there is the x-intercepts. Again, I can just move my little bug around to see those x-intercepts. The first one looks like it's at about, oh, it's terribly zoomed out, but it looks like it's about at 6. And the next one looks like it's about at 9. And then, yes, there is one that we can't see over here. It's going to go down this way. Okay? That's going to be in the negatives. So, looks like we're going to have, for our x-intercepts, negative something. I don't really care what that one is. I'll explain why I don't care what that one is here in a second. We had one at 6, and we had one at 9 for the x-intercepts. So the reason that I don't care about that negative something is because does this make sense in terms of our problem? No. We wouldn't be able to cut out a negative, right? So we're not going to be able to see cutting out a negative square doesn't make any sense. So not caring about that. This is the only section of our graph makes sense, and actually only part of that section makes sense. So next, our y-intercept. So if you move your little bug over, this calculator is older than most of you, I'm realizing. Looks like it's at 0. Huh, that must mean that our other x-intercept that I thought was negative something isn't. It's 0. What happened when we cut something out? Our y-intercept is also at 0. It crosses exactly at the origin. Okay, and our domains, you might remember, our domain is talking about our x values. So domain, all of our x values. Now, for our graph, we decided how far that we could see in that domain, but we know that this is going to go down. It's going to keep going forever. It's going to keep going up and keep going forever. So our domain is going to be all real numbers. Which we have a shorthand for. Our shorthand for this is an R with like an extra slash through it. It just means all real numbers. It's going to go left and right forever. That's all that says. Okay. Now our range is all of our y values. We'll label that here too, in case we forgot. Y values. If this graph is going to keep going, and it keeps going down forever and ever, and this one keeps going up forever and ever, that means our y values are also all real numbers. It's going to keep going down and up forever. So I will do our all real numbers sign now. Okay, and this last question, what is the maximum volume of the planter? And we're going to state the dimensions. So when we look at our graph, just like that drain situation, we can look at our maximum, because it's going to be right up there. Somewhere up there. It looks like it goes down. Cool. This seems to be about our maximum right at the top here, and our dimensions, well, at least our x, our height, is going to be 2.3-ish. That's our height. And we can figure out our width and our length by using that expression we came up with. So 18 minus 2h, right, to get us our width. And we know that our height is 2, so take away about 4, it's going to be about 14. Oh, you guys can't see that, sorry. And then our length, same idea, but 12 minus 2h, so about 8. Okay. Our volume, our maximum volume, is going to be at that 228. Max volume at about 228. Cool. Let's go ahead and pause here for a second. We're going to flip our papers over, our notes over, so we can move forward. Alright, in your guys' notes you've got some place for some vocab. So here that is the relative maximum is the highest point on a particular section of a graph, and the relative minimum is the lowest point at a particular section of the graph. I've got this unrelated example over here. So if we were to look at a relative maximum, that's going to be this point right here. Okay, that's our relative maximum. It's the highest point. I also call these like turnaround points. So that's got a turnaround point there. okay? And it's obviously a maximum. The reason that it's a relative maximum is because if you look over here, there's a place that's higher than this. But compared to the points around this point, that is the highest point. So it's a relative maximum. Relative minimum, same idea except backwards. So it's the lowest point in a section, which means it's right down here. Now again, there's clearly some that are lower than that point, but that's the lowest section in that part of the graph. Okay. So for this question here, on your graph of the volume function, find that relative maximum and relative minimum. Go back in your notes and label those as relative max and relative min. On your guys' graph that you put in your notes, your scale might be a little bit different than mine. This should be the general shape that we've got. And so hopefully we've labeled our relative max there and our relative min there. Cool. We're going to use that graph for our next few questions. So first question, a customer ordered a particular planter box with a volume of 100 cubic inches but didn't specify the height. Use your graph of this situation to answer the following questions. What height will the volume equal 100? So when will y equal 100? And then B, how many different planters will have a volume of 100? Go ahead and pause the video and see if we can answer that one. Because we were wondering when the volume will equal 100, I'm going to go ahead and put a line at that place. So here's the volume of 100 we were looking for. And I'm just going to draw a line across there. Okay, so you can see that if I extended my graph a little bit, that crosses 3 different times. Here, here, and here. Now, the problem is anything past 6 we said didn't make any sense. So this down here doesn't make any sense in terms of our problem. This up here doesn't make any sense because we can't take more than 6 inches away from both sides. Because our box was only, our original sheet was only 12. So as soon as we went over 6, we've taken it all the way. It's no longer a planter. Okay? So to answer our question, what will the height be when we equal 100? Well, it looks like we're at 1 inch there and maybe about 4.5 inches. I'm not looking for us to be super particular, but down here, when will the height equal, or what will the height be when the volume is 100? The height will be 1, and we have another option at 4.5. And how many different planters will that be? Well, clearly that's 2. Yes, there are other places on our graph where that happens, namely here, but this section of our graph doesn't make sense. Okay, let's go ahead and look at our next question. This one's on the next page of your guys' notes. It says, a neighborhood beautifying committee would like to purchase a variety of planter boxes with volumes of 175 cubic inches to be added to business windows, windowsill storefronts. Determine the planter box dimensions for Plant-A-Seed Company can create for the committee. Show all your work and explanation. So similar idea, but we're looking for 175 cubic inches. Go ahead and pause the video and see if we can answer that one. If we're looking for a volume of 175 cubic inches, that's where I'm going to mark my graph. Just following my green line there. Yes, there's another place over here where it crosses, but we know already that that makes no sense for our problem, so I'm not going to draw it. If we follow this down, it looks like that happens at about 1.5 and maybe 3.5. So when we look down here, on the next page, we've got height of 1.5 and height of 3.5. And then we also want to figure out the width and length. So we know the width is 18 minus 2h, and the length is 18 minus 2, or I'm sorry, 12 minus 2h. So that would be a width of 15 and a length of 9 for that first one. For the second one, the width would be 11 and the length would be 5 for the second one. Alright, and that's it. It's the end of 5.1. You guys have DOL and then homework to work on. Hopefully if we didn't get any of this, we can talk to our friends around us and they will help us out. But let's go ahead and take a look at that DOL just in case there are any questions on that. So question 1 and 2, well, for all questions, you're identifying the relative maximums and relative minimums. There might be more than one relative max or relative min, so just be on the lookout for that. For 1 and 2, I gave you equations, which means you're probably going to want to throw those in a graphing calculator. You will have to change your windows, though. There's very little chance that these are going to fit in the same window we had before. So you're going to have to change your windows. So for 1 and 2, put them in a graphing calculator, change your windows, and we're looking for relative maximums and relative minimums. For 3 and 4, I gave you the graphs, so you just need to identify where those are. Alright, go ahead and work on your DOL, and then work on your homework for me.